Hello, this is the 23rd video on my multivariable calculus. In this video, we're going to talk about change of variables. We have learned before how to do double integrals in Cartesian coordinates as well as polar coordinates. In this video, we're going to talk about how to switch from Cartesian coordinate to a completely arbitrary coordinate system. So what is the general strategy? And then we're going to do some examples. So the first thing is that when we switch from a coordinate system like xy to a new coordinate system uv, what we have to do is we have to replace dA by the absolute value of the Jacobian times du dv. This factor is the one that allows us, the Jacobian factor is the one that allows us to switch from dA to du dv. Now, what is the Jacobian? It is evaluated by this determinant. It's partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, and partial of y with respect to v. And then we'll have to evaluate that determinant. For example, if you look at the polar coordinates, x is r cosine and r cosine of theta, and y is r sine of theta. So if you look at the Jacobian, this is the Jacobian of xy relative to r theta. We get partial of x with respect to r, which is cosine, partial of x with respect to theta, which is negative r sine, partial of y with respect to r, which is sine, and partial of y with respect to theta, which is r cosine of theta. And evaluating that, we get r cosine squared of theta plus r sine squared of theta, which is exactly r. And this is exactly the polar factor that we learned we have to use when we go from dA to dr d theta. So dA is r dr d theta. One other thing that could be helpful is that the Jacobian of xy relative to uv and the Jacobian of uv relative to xy are reciprocals of each other. So sometimes that helps us in calculation. So now let's look at a few examples. Evaluate the double integral over r of x dA, where x is the parallelogram with vertices 0, 0, 1, 2, 2, 1, and 3, 3. So the first thing we're going to do is we are going to graph the region as usual. So we have 0, 0, 1, 2, 2, 1, 3, 3. So I'm going to mark the two axes, 1, 2, and 3. So 1, 2 is right here, 2, 1 is right here, and 3, 3 is right here. Okay, so it's a parallelogram based on these four vertices. Now, if you look at this parallelogram, can we do this one using dx dy or dy dx? The answer is really yes, but we'll have to break this up into three different regions. This one is a vertically simple region. This one is also a vertically simple region, and this one is also a vertically simple region. So it's possible to do it this way, but it would be quite complicated. So instead, what we are going to do is we are going to switch to a different coordinate system. So what does that mean and how do we achieve that? Well, if you think about the usual graphing paper is x equals constant. So these are our vertical lines, and then y equals constant. These are our horizontal lines. And those lines would divide this one into three different regions that are vertically simple. But if we look at lines that are like this, these lines perfectly fit region. So if we change our grid into these lines and also these lines, this region is going to be much easier to deal with. So what do we mean by by these lines that are not vertical or horizontal? Well, we can find equations of these lines. For example, this line right here is y equals 2x because the slope is 2 and the intercept is 0. This one is parallel, so it would have the same slope, and it passes through 3, 3. So when you plug in 3 for x, you have to get 3 for y, which means we have to subtract 3. So how can we describe these red lines? They are all y equals 2x plus a constant. So what we can do is we could say if we take u equals y minus 2x, then in this region, u goes from 0 to -3. So I would have to put the -3 on the left. So that's those red lines. Now, if you look at the blue lines, and I'm going to turn this one also blue, then what is the equation of this one? This one is y equals 1/2 x, because it goes through the origin and the slope is 1/2. And this one is parallel, so slope is 1/2 still, but it also goes through 3, 3. So if you plug in x equals 3, we have to get y equals 3, so we get 3/2. So what would be a good variable for the other one? Well, if you think about these blue lines, they go from y minus 1/2 x equals 0 as the bottom one to y minus 1/2 x equals 3/2 as the top one. So these are the blue lines, the parallel blue lines. So this is a change of variable that we're going to use. So now, how do we do that? Well, first of all, we are given this limits of integration for this new u and v. We figured it out here. So u is between -3 and 0, and I'm going to draw a diagram for uv. So u equals -3 to 0, and v equals 0 to 3/2. So this is our new region. So what does it mean? It means we were able to successfully change a parallelogram to a rectangle. Now we will have to find a Jacobian. So what is the Jacobian? We just saw that the Jacobian should be evaluated by partials of x and y with respect to u and v. Unfortunately, we do not have x and y in terms of u and v. We could just solve this system and find x and y in terms of u and v, or we could do 1 over the Jacobian of uv with respect to xy. And let's evaluate that. So this is 1 over. So the first one is partial of u with respect to x, partial of u with respect to y, partial of v with respect to x, and partial of v with respect to y. So we're going to plug in the values and we're going to evaluate the determinant. Finally, we'll have to take the absolute value. What is partial of u with respect to x? That's -2. Partial of u with respect to y, that is 1. Partial of v with respect to x, -1/2. And partial of v with respect to y, which is 1. So this would be 1 over -2 plus 1/2, which is -2/3. So this is the Jacobian. And all we gotta do is to do the du dv, but we have to multiply by absolute value of -2/3, which is 2/3. Now, looking back at the original integral, we also have an integrand of x, so we'll have to solve for x. So we need to find the integrand, which is x in this case, in terms of u and v. So the integrand was x. So how do we get x from this equation that we have right here? Well, one way would be elimination. So we could subtract the two equations and eliminate y. So if we do that, we get u minus v equals -2x minus 1/2 x, or I believe it should be plus 1/2 x. And this is -3/2 x. So from here we get x equals -2/3 times u minus v. So the double integral over r of x dA is going to be, so x is -2/3 u minus v. This is x. This is the integrand. Then the Jacobian, so absolute value of, so what we got here, which is -2/3. And then the region in the UV plane is a rectangle, so we could just simply do du dv or dv du. Both of them are going to work. So what are the limits of u? -3 to 0, and limits of v are from 0 to 2/3, I believe. Yeah, 3/2. Okay, and finally we'll have to evaluate this integral. This is a pretty easy integral to evaluate. Okay, so next example. Find the volume of the solid that lies below the graph of z equals x squared plus y squared and above the region in the first quadrant of the xy plane bounded by these curves. So in the xy plane in the first quadrant, so let's graph the region. Okay, so xy equals 1, xy equals 2, y equals x, and y equals 2x. So this is the region that they gave us. So this is our region. Clearly, this region is not a vertically simple or horizontally simple region. It's pretty complicated, the region. You can divide it into multiple regions that are vertically simple and horizontally simple and evaluate it that way. But we could also use change of variables. So let's first write down the equations here. So this is y equals x, this is y equals 2x, this one is xy equals 2, and this one is xy equals 1. Okay, so volume of the solid above this region and below this. So we know that the volume would be double integral over this region, let's call this region R, of the height of x squared plus y squared. Now we will have to evaluate this one using a change of variable. So what change of variable is appropriate? So we're going to do something similar again. So if you look at the lines here, the lines are y equals x. So we can kind of think about these as these lines through the origin. Our grid could be these lines. This line through the origin. So the first one is y equals x. The next one would be y equals 1.1x, 1.2x, etc. So what would be a good appropriate change of variable here? Well, one appropriate change of variable would be y equals u equals y over x, because then the first one is u equals 1, y equals x is u equals 1, and the last one y equals 2x is u equals 2. Now, how about the other side of the other like grid lines? Well, this is xy equals 1, xy equals 1.2, xy equals 1.5, etc. So these are the curves that we can look at. So we could think about those as v equals, and let me write it down here, v equals xy. Now, if we do that, then that tells us u is between 1 and 2 based on the fact that y over x is equal to 1 and y over x is equal to 2. Those are the two boundaries of the region. And on the other end, you have xy equals 1 and xy equals 2. So these are the limits of integration for when we switch to x and u and v. Next thing we're going to do is to evaluate the Jacobian. So partial of xy with respect to uv, we'll have to evaluate x and y in terms of uv and find their partials. Although because we have u and v in terms of x and y, it is better to do the reciprocal. So we will do that. So that's 1 over partial of u with respect to x, that's minus y over x squared. Partial of u with respect to y, 1 over x. Partial of v with respect to x, partial of v with respect to y. So that would be 1 over minus y over x. If we multiply the two y over x squared and x, we get y over x minus y over x. And we'll have to write down everything in terms of u and v. So that's 1 over minus. So now y over x is u, so we get 2u. So this is the Jacobian. And we will have to also take the absolute value of this one. Next, we'll have to find the integrand, so x squared. So how do we get x squared from these two? We'll have to solve for x and y. That's pretty simple. If we multiply the two, we get y squared. So uv is equal to y squared. If you multiply the two, u equals y over x and v equals xy, we get y squared for uv. And if we do v over u, we get x squared. So that means double integral over r of x squared plus y squared, which is the volume that they asked us to evaluate, is going to be So x squared is v over u, y squared is uv. Then we'll have to multiply by the Jacobian, so absolute value of 1 over negative 2u. And then we know that the region is a vertically simple and a horizontally simple region. So we could do du dv or dv du. So this region is in fact just a square in the uv plane from 1 to 2. So this is our new region. And the two limits of integration are 1 to 2. So this is our integral. And this is not a very difficult integral to evaluate. I'll write down one more step, but I'll let you evaluate the integral. So we can take out the 1/2 and put it in front. So I'm going to do that. And then absolute value of 1 over 2u is just 1 over 2u. So we don't need the absolute value anymore, dropping the negative sign. Then we get v over u squared plus v. And then we'll have to do du dv. And this is pretty easy to integrate. One more example. Find the area of the region enclosed by the ellipse where a and b are positive constants. So let's do that. Okay, so how do we parameterize the inside of the ellipse? Well, the way we can parameterize it is we can use a sort of a polar coordinate. Polar coordinate wouldn't quite help here because polar coordinate you would need a circle. But what we can do is we could say if we look at x over a squared plus y over b squared, inside the ellipse, this is less than or equal to 1. So what does that mean? It means we can use a kind of a similar, something similar to a polar coordinate. So x over a would be r cosine theta, and y over b would be r sine of theta. Now, what are the limits of r? Because here I have 1, limits of r would be from 0 to 1. And because it's a complete ellipse in all different quadrants, theta would go from 0 to 2 pi. Now from here we can get x and y, so we would get x equals ar cosine of theta and y equals br sine of theta. Now, one thing that I forgot to mention at the beginning is that since we are trying to find the area, we do need to use double integrals. So what is area? Area is double integral of 1 dA. So this is what we're trying to evaluate if I call this region R. Now, in order to evaluate this one, we'll have to first find the Jacobian. So let's find the Jacobian of xy relative to r theta. In this case, x and y are given in terms of r and theta, so we don't need to do reciprocal. So it's a cosine theta minus ar sine theta, b sine theta, and then br cosine of theta. So when I evaluate this, this is going to be abr cosine squared theta plus abr sine squared of theta. So factoring abr, we get abr times cosine squared plus sine squared, which is just abr. And since a and b and r are positive, I don't really need the absolute value. So area becomes abr dr d theta. And we discussed why r goes from 0 to 1 and theta goes from 0 to 2 pi. And this is a very easy integral to evaluate. And hopefully at this point you actually know what the area of an ellipse is so that you can kind of check your answer. So this would be an integral from 0 to 2 pi. And then when you plug in 1, we get ab over 2 d theta, because at r equals 0 we get 0, and this is going to be ab pi, which is in fact the area of an ellipse. I will do one last example and then we summarize what we did today. Okay, so evaluate this double integral where r is the region bounded by the y-axis and the lines y equals x, x plus 1 equal x plus y equals pi over 4. This is a bit of a different type of example. So y equals x, this is the line, and then x plus y equals pi over 4. So this point is pi over 4 comma 0, and the y-intercept is 0 comma pi over 4. So we have y equals x, x plus y equals 4, and the y-axis. So this is our region. Okay, so when we want to evaluate the integral over this region, we could identify this region as a vertically simple region, in fact. This is certainly a vertically simple region. So now, if we were to evaluate that, so we would get sine of x plus y over cosine of x minus y dA. Okay, so this is y equals x. So the intersection of these two would be pi over 8. So we could do, because it's a vertically simple region, we could do dy dx. Now, what are the limits of y? The limits of y are from bottom, which is y equals x, to top, which is y equals pi over 4 minus x. And limits of x are from 0 to pi over 8. Okay, now the problem starts. The problem is, how do we integrate this expression inside the integral? So how do we evaluate this integral? And this is not impossible, but it's a pretty difficult integral to evaluate. So because of that, we're going to use a different strategy. Even though the region is a nice region, but the integrand is not nice enough for us to be able to evaluate the integral. So we're going to use a strategy to change the integrand. In other words, we're going to choose a change of variable that makes a change in x plus y and x minus y. Now, the benefit of that is that it also changes one of the boundaries to u equals pi over 4. So this may not work. So this is the solution number 1, which is difficult to integrate. Okay, so because of that, we will try something else. So here is the second attempt at solving the problem. So we will use u equals x plus y and v equals x minus y. Why do we do that? Because we make the integrand simple. To simplify, in this case, not the region, but the integrand. Okay, so let's now look at the region. So we know that integrand got simplified. Let's look at the region. So what is the region? One of the sides is x plus y equals pi over 4. So this becomes u equals pi over 4. One of the sides is y equals x. So y equals x becomes v equals 0, because that's just x minus y. And one of the sides is x equals 0. So x equals 0 becomes, so we'll have to understand what is x equals 0. Well, we have to find x from here. From here, x is going to be u plus v over 2. So that's x. So this is going to become u plus v over 2 equals 0, which is u equals negative v. So we can draw this region in the uv plane. So let's do that and see. Hopefully the region is not too bad to work with. So one of the sides is u equals negative v. So I'm going to draw it right here. So this is u, this is v. One of the sides is u equals negative v. One of them is v equals 0. So it is this one. It is this one. And one of them is u equals pi over 4. So we'll have to extend this one on this side. So it's in fact on this side. It's not on that side. V equals 0 and u equals pi over 4. So this is our region. This side is u equals negative v. This one is u equals pi over 4, and the other one is v equals 0. So this is our region, in fact. So this is still a nice region. So I'm going to call this new region S. Now we'll go ahead and evaluate the Jacobian. So partial of xy with respect to uv. This is going to be probably easier to use 1 over partial of uv with respect to xy. This is going to be 1 over, so partial of u with respect to x, well, u is x plus y, so both partials are 1. Partial of v with respect to x is 1. Partial of v with respect to y is negative 1. So this is going to be 1 over negative 1 minus 1, so that's negative 1 half. So that means the double integral of sine of, let me go ahead and see what the problem was, sine of x plus y over cosine of x minus y dA over the region R. So this is equal to, this is a vertically simple region, so we could write it down as sine of VU over cosine of V. Because it's a vertically simple region, we do dV du. Now what are the limits of V? Bottom is negative u, top is 0, and limits of u are from 0 to pi over 4. So when you integrate with respect to V, sine of u is constant, so we can take it out. So this is 0 to pi over 4. Sine of u is constant. And when we substitute, when we integrate secant of v, so this is secant of v. So integral of secant of v is going to be natural log of secant of v plus tan of v. And then we'll have to substitute v equals negative u to v equals 0. And then this is du. So once you want to evaluate this one, you see that this is going to get a little bit complicated once you plug in negative v. So this is going to be a bit complicated. So instead, what we can try is we can try this region as a horizontally simple region. So instead of doing the integral of this one as a vertically simple region, we could try this as a horizontally simple region. So let's try that and see what we get. We get the integral sine of u over cosine of v. Now we do du dv rather than dv du. When we do du dv, we could say u goes from here to here. Well, u goes from negative v to pi over 4, and v goes from negative pi over 4. So this point is negative pi over 4 to 0. So let's try that and see if that works better. Okay, so now integral with respect to u is actually pretty easy. So this is negative pi over 4 to 0. When you integrate sine of u, we get negative cosine of u over cosine of v. Then we'll have to plug in u equals negative v to u equals pi over 4 dv. So we get negative pi over 4 to 0. If you plug in pi over 4, we get negative cosine of pi over 4 over cosine of v minus cosine of negative v over cosine of v dv. Now, cosine of pi over 4 is root 2 over 2, so this is integral from negative pi over 4 to, and then the integrand is negative root 2 over 2 cosine of v. There's 2 minus signs, so that's plus. Cosine of v over v is 1 dv. Okay, so this is definitely easier to evaluate. So this is going to be integral from integral is going to be negative root 2 over 2. Integral of secant is natural log of absolute value of secant plus tangent plus v from negative pi over 4 to 0. And the rest is just substituting the values. So as you see, this integral was actually a pretty difficult one. So we had to do a couple different attempts until one of them worked. So what is the general idea of change of coordinates? When switching from xy to uv, we evaluate this by following these steps. First thing is always to sketch your region. Then you choose an appropriate u and v if your region is not a vertically simple, horizontally simple, or polar region. You write down the integrand in terms of u and v, find the Jacobian, and find the limits of your u and v by drawing the region in the uv plane, find the Jacobian, and then evaluate the integral. I will see you in the next video.